This is the Chem 1 lecture over both density and graphing. So density is a physical intensive property that is a way to look at both mass and volume. So it's a ratio of mass to volume. So the closer the molecules are to a given volume, the greater the object's density would be. So the closer those molecules are packed together, it's going to be more dense. It's intensive, it's independent of amount, but it's also unique, so we're actually able to use it to identify some kind of unknown substance. So some of you guys may have done density calculations before, and you might learn that density is equal to mass of whatever substance over its volume. So those are options, units. There's a whole variety of units that could be. It could be any unit of mass divided by any unit of volume. So one you're going to see pretty frequently in here would be grams over milliliters, since those are both metric units. You may see something like grams per centimeter cubed. Centimeters cubed is another unit of volume, but you may have crazy English units. So what if we had pounds per gallon? You won't see that too often in here, but that's still a mass over a volume, so it still counts as a unit of density. So let's go through and think through some conceptual ideas about density before we go through and do some math. So up here I've got two boxes. I got box A and box B, and I got some red balls in there. That's all I know. And the question is, which block has a greater mass? Well, I would choose block A since it has more of those red balls in there than B. But which one has a greater volume? Let's look. Well, the size of these boxes, they look very much the same. Since they're the same, that means the volume is the same. So next, which block has a greater density? Well, since block A has more stuff for the given volume, I would say that A is more densely packed. Let's see the next one. Let's see, we've got this block, and it says if it were cut in half, what would be the relative density on both halves? And we're actually given some numbers. So our first block, I know the mass is 200 grams and the volume is 100 centimeters cubed. So the density would end up being mass over volume, 200 grams over 100 centimeters cubed. That is, what is that, 2 grams per centimeter cubed. Let's look over if we cut the block in half. Okay, so we have 1/2 of it over here. Let's see, the mass would be halved, so we would have half as much mass, 100 grams, and half as much volume. So the density would then be 100 grams divided by 50 centimeters cubed. Guess what? The density would be the same, 2 grams per centimeter cubed. The halves would be the same. So the way I think through that is I know density has to do with how closely packed those particles are. So if I took something like a block and I cut it in half, did I squish those particles closer together, or did I expand them? I didn't, right? Those particles are still the same distance apart, I just have less of them. But if I have half the mass and half the volume, I ended up with the same density. So this is where you can see that mass and volume are extensive properties. Those do change when you change an amount, but when you put them together into density, you actually end up with an intensive property, something that's independent of amount. So next we've got some density problems. We are going to be using dimensional analysis again, that way we can get any kind of unit conversion done in with the math. We are actually not going to do algebra on these, so I'm going to expect to see density done with dimensional analysis. So our first example, a rectangular piece of cement has the dimensions of 2 by 2 by 3 centimeters. We need to calculate that density in grams per centimeter cubed, and we're given that the mass is 0.108 kilograms. So first, if we've got these dimensions, we need to find the volume. So remember, the volume is going to be length times width times height. So in this case, it's going to be 2 centimeters by 2 centimeters by 3. So we've got to take all 3 of those dimensions and multiply them together. I'm going to ignore sig figs for a second. 2 times 2 times 3, let's see, 2 times 2 is 4, times 3 is 12 centimeters cubed. And let's see, we have 3 sig figs in each number, so I need 3 sig figs in my volume. So there's half of my problem. I know density is mass over volume, so I'm going to have to start my t-chart with mass on top. So I'm going to start with my 1.108 kilograms on the top per 12.0 centimeters cubed on the bottom. This is a unit of density, but it is kilograms per centimeter cubed, and we needed to find grams per centimeter cubed, so we don't quite have the right units yet. So you got to keep chugging along here. We got to cancel out my kilograms, so I'm going to put it down there on the bottom. And let's see, converting kilograms to grams, that is a conversion you're supposed to know. For every 1 kilogram, we have 1,000 grams. So once we do that, our kilograms are going to cancel out, so our units are going to be grams up top, centimeters cubed on the bottom, which is matching the units we needed to find. So once we do the math, so we're going to take 0.108 kilograms times 1,000 divided by 12, we're going to get 9. Now, that's not the right number of sig figs. If we go back to the problem, we have 3 sig figs in our numbers, so we need to add 0.00 after our 9 to get 3 sig figs, and the units are going to be grams per centimeter cubed. So, an example number 2, let's see, gold has a density of 19.3 grams per centimeter cubed, so we're given density. We're asked to find the mass in pounds of 7.25 centimeters cubed of gold. So in this case, we have density, so we need to think about density as a conversion factor. So that means if I have 19.3 grams of gold, it's going to occupy or equal 1 centimeter cubed of volume. So that density is going to be a way for us to convert between mass and volume. So we're going to start with our other number. We're always going to start our dimensional analysis with whichever number has fewer units. So it's going to be 7.25 centimeters cubed. Got our T-chart here. So I know I need to cancel out my centimeters cubed, so I'm going to put that down there on the bottom. And if we go back to our density, I know 1 centimeter cubed equals 19.3 grams of gold. So at this point, we have canceled out our centimeters cubed, and we have grams, which is completely a unit of mass, but not the unit of mass we were asked to find. We're actually asked to find pounds. So we need to keep on going. So I'm going to extend my T-chart here. Got to cancel out my grams. I'm going to put it on the bottom. And this time we were asked to convert it to pounds. So if you weren't sure what the abbreviation for pounds were, you could write out the word pounds. I happen to know that it's LB. And let's go back. We're given that conversion factor up here in the problem. I see 1 pound. 1 pound is 454 grams. So now that we've done that, grams are going to cancel out, and we're left with pounds, which is what we were asked to find. So now it's just a matter of doing the math here. Multiply across the top, divide by the bottom, so 7.25 times 19.3 divided by 454, that's going to give you 0.308 pounds. Same thing, let's go back to the problem. Each number has 3 sig figs in it, so since we multiply and divide, we need to round to our least number of sig figs. So in this case, it would be 0.308 pounds. So our third example, let's see, the density of sulfuric acid is 1.84 grams per milliliter, so we're given density, and this time we're given mass. We know the mass is 25 grams, we're asked to find the volume in liters. So same thing as before, I'm going to really think about density as a conversion factor. So 1.84 grams of sulfuric acid would take up 1 milliliter of space. I'm going to start my dimensional analysis. I've got 2 numbers in the problem. I'm going to go ahead and use the one that has fewer units, 25.0 grams. That's what we're going to start with, 25.0 grams. Dimensional analysis, same thing. I know I got to cancel out my grams. I got to throw it down there in the bottom. Well, we've got, we can go ahead and use density since that has grams in it. We can go from grams to milliliters, and that's 1.84 grams for every 1 milliliter. So when we do that, we've now canceled out grams, and we have milliliters, so we have volume already, but we were asked to find volume in liters, so we're not quite done yet. Got to keep going. Cancel out my milliliters, and we can actually go between milliliters and liters. That is a conversion factor, that prefix milli. If you remember, that means 1,000th, so that means there's 1,000 milliliters for every 1 liter. So now that we've done that, milliliters cancel out, we're left with liters. That's what we were asked to find. So now we just need to do the math here, multiply across the top and the bottom, and then divide. So it'd be 25 divided by, and then important, be sure you put your denominator in parentheses since there's more than one of them, 1.84 times 1,000, and you're going to get a pretty small number here. You're going to get 0.0136 liters. So same thing, the numbers in the problem were multiplied and divided, so we need to round to our least number of sig figs, which was 3. There we go. So remember, we're going to do density in here as dimensional analysis. That way we get all the algebra and all the converting done in one math step. So for tests, you do need to use dimensional analysis on these. The next thing we're going to talk about is graphing, and I realize most of you guys have made graphs before, so some of these rules might be familiar to you guys. Things like if we give you graph, usually we won't make you use graph paper, we'll just give you a little picture of a graph like you have in your notes. You need to at least fill up half that graph paper. You need to utilize the space. If we give you a graph that's half the page, don't give me a graph that's 1 inch in size, teeny tiny. So you do need to think about what those tick marks need to be, what the value needs to be. So an easy way to do that is to count how many you have and figure out what they need to go by. Divide by the range of your data that you're going to graph. Be sure you label your axes. So X and Y axes need to have whatever it is, so like mass, but also units. So is it mass in pounds or mass in milligrams? You do need to have that. Typically that's given in parentheses. You do need to have a descriptive title. The title does need to describe whatever data you're graphing, whether that means it's distance versus time, or if you want to be specific and talk about what that slope is. Well, if you're graphing distance and time, your slope is actually your speed. And you also need to have a line of best fit. So that's either going to be a straight line or a curve. In science classes, you're never going to play connect the dots between your data points, but you're always going to see the trend of the data and draw either a straight line or a curve through as many points as possible. And that way, again, when doing an experiment, you can kind of ignore those outlier data points that we may get. So in class, we went through and everyone collected some data points. So I grabbed some data from the website. So I've got 8 cups here, and I'm looking at the table over here. So I've got my 8 cups. I've got a volume of zinc, and I have a mass of zinc. So we're looking at density here because we have mass and volume. So important terms, so independent and dependent variable, and you've got these guys on your notes also. Those are important vocabulary terms for you to know, so graphing terms here. Independent variable is the one that's controlled. That's the one that the scientist changes, and it always goes on the x-axis, while the dependent variable is the one that changes. So it's usually the one that they're measuring as the experiment happens, and that always goes on the y-axis. So be mindful of those vocabulary terms. So what I did was I counted the number of tick marks I had on the graph, and I noticed that the x-axis, so we needed to put volume on the x-axis, and that the points went from 2 to 20. So I went through, and I think there's 22 tick marks here, so we could have used one for each of them. I did want to condense my graph a little bit, but I still used over half of it. And then same thing on the y-axis. I noticed my data points went pretty much from 0 to 100. So I made every other tick mark worth 10, or them worth 5. So what you could do is take the number of tick marks and divide it by your values, and we got about 5 per tick mark. So then I went through and I numbered them, and they're evenly spaced, and I went ahead and labeled the axes. So I put what the unit, what the value was for each axis, but also the unit. So it's not just volume, but volume in milliliters. Also notice I've got a title. I happen to know if we're looking at the slope of this, so it would be the change in y over the change in x, it's going to be mass divided by volume. I know that that's density. If you weren't sure, you could just say volume versus mass of zinc. That's still a title that describes that graph. So then I went through and I plotted the points here, so you can see the little dots on the graph as I go. And then I noticed that they pretty much make a straight line, but it's not perfect, so I got out a straight edge, so an edge of a paper or calculator or ruler, and I tried to draw a straight line that goes through as many points as possible, but obviously I didn't hit all of them, and that's okay. That allows for some outliers in a scientific situation. And I've circled 2 data points here. So I've picked out this graph point up here, which is the last one, and I picked one that is not actually a data point, but that actually hit 2 points on the line here. So here are going to be my 2 points. So if you wanted to write them out, that means, let's see, our first data point we used was this guy right here. And then our second data point would be actually, what is that, 35 grams and about 7.5. So when we pull a list of vocabulary, there's two I haven't talked about yet, and it's interpolation and extrapolation. So it has to do with predicting or making new data points based on your graph. So if you're interpolating, the prefix inter means within a set of data points. So for example, if I wanted to figure out, if we wanted to find on our graph here, we wanted to know, let's see, what is that, 16.5 milliliters. We could go up here, go up and over. We could figure out how many grams that would be. And since that's within our data points here, that's considered interpolation. It's between them. Extrapolation, prefix extra means outside. That means it would be outside the data points. So let's say, let's see, our volume of zinc ends at 20 milliliters, but what if we wanted to know how much 24 milliliters would weigh? Well, if we went to 24, we had to extend the line here, we could go up and over, we could figure out about what that volume would be, but since it's outside of our known data points, it's considered an extrapolation. So if we look at our graph, well, 1 is outside our data points, right? Our last data point was 2. Oh, wait, nope, it was 3.44 grams. So we come over here, and 1 would be outside our data points. We could figure out what it crossed over, and I'd say, I mean, this is a real big estimate, maybe half a milliliter. That is a big 4 milliliters. Okay, that's within our data points. We could go up and over here. And I'd say it's under 20. So you can notice we've got a few questions we need to answer. So first of all is to determine the experimental density by calculating the slope of the best fit line. So you can see that y'all have done slope probably in other classes, that it's the change in y over the change in x. Or what is it? Rise over run. That's what they're always told. So I need to pick 2 data points. So let's go back to the graph. Add in to our problem here. We're going to end up with 95.43, so that's y2 minus y1, which we said was 35.00, not using units because I'm running out of room, divided by x2, so that's grabbing one from the data table here, so that was 95.43 was 20, minus the other one, which we grabbed, let's see, at 35, it was 7.5. So when you do the math here, you're going to get 60.43 over 12.5. Use your calculator to do the math, and you're going to get 4.83 grams per milliliter. Well, we know that the next question, the accepted density of zinc is 7.14 grams per milliliter. So now we find the percent error, which sounds really scary. We do have a formula here, so it's going to be experimental minus the accepted divided by accepted, and they got dropped off here, but there should be little absolute value signs there. We want to be sure that's a positive value. So we got, in the experiment, we got 4.83 grams per milliliter, but we should have gotten, the accepted is 7.14, so minus 7.14 divided by 7.14, absolute value, times 100 to make it a percent, and we're going to get 32.35%. So next 2 questions have to do with a couple of new vocabulary terms. So if you go back, question, based on your best fit line, what volume would 1 gram of zinc take up? We're actually going to have to estimate though. So I'm going to do a squiggle there because I'm really not sure on that, but 0.5 milliliters. Since it's outside of our data points, it's an extrapolation. So then what if we wanted to find the mass of 4 milliliters? Well, so let's say it's about 18 grams. And then so since that was within our set of data points, it would be an interpolation.